Algebra 2, Lesson 7-3, Independent and Dependent Events. So sometimes in probability, we look at more than one event at a time, and sometimes they happen independently of each other, and sometimes the second event will depend on what happened on the first one. So that's a quick overview. Now we're going to talk about each of those more detail. Independent events are events whose probabilities do not affect each other. For example, if I roll a die and flip a coin, they're not going to affect each other. To find the probability of two independent events, we basically just apply the fundamental counting principle, which says I find the probability of the first thing happening, the probability of the second thing happening, and then I multiply them together. So let's go ahead and do a few examples. What is the probability of spinning a 4 and then spinning a 4 again? Well, the probability of spinning a 4 on this spinner is 1, 2, 3 out of, how many sides does it have? 8. Okay, then when I go to spin the spinner again, it's not like I've used up one of the 4s, they're still there. So the probability of getting a 4 again is also 3 out of 8. So all I need to do is multiply these two probabilities together. I get 9 out of 64. Which is approximately 0.1406. So fraction or decimal, there you go. What is the probability of flipping a coin and getting heads 3 times? So I'm going to flip this coin 3 different times in a row. First flip, what's the probability of getting heads on a flip of a coin? It's 1/2. Then I flip it again, 1/2, and I flip it the third time. Oops, I wrote a 3, but I meant 1/2. So then we multiply that together and we get 1/8, which is 0.125 as a decimal. All right, here's one with pens. So Amanda has 20 red pens and 30 black pens. What's the probability that she picks a red pen, puts it back, and then picks a black pen? So the putting it back is very important because that will be the difference between it being independent, not affecting each other, and dependent. So the probability of getting a red pen is 20 out of 50 total pens. And then we put it back. So now there's still 20 red pens, 30 black pens. What's the probability of getting a black pen? 30 out of 50 because they're all back in there. And then we just multiply those probabilities together, reduce our answer, which would be 6 over 25, and then divide that and it's 0.24. All right. So moving on to dependent events, dependents do affect each other. So what happens on the first event might change the outcome of the second. So here's the notation. The probability of A and B both happening is the probability of A. So you find that first. And then you multiply it by kind of the what's left over thing. So the probability of B given that A already occurred. So we'll talk a little bit more about that as we do some examples. So let's do this. First, explain why they're dependent. So 2 number cubes are rolled. One's red, one's blue. Find the probability that we have a red 1 and the sum is less than 4. So the probability that we have a red 1 happens right here. The probability of a red 1 is 6 out of 36 or 1/6. Okay, what's the probability that the sum is less than 4? Well, the sum is less than 4 is these add up to 4, which I don't want. So just these 3 answers are less than 4. But I already counted some of those because they're red 1s. So what I need here is given that we already have a red 1, how many of these have a sum of less than 4? So out of these, there are 2 of them with a red 1 and less than 4. So there are 2 out of the 6. Out of the ones that, so we narrowed it down first to these 6 that we could have, and 2 of those are the ones that we want. So I'm just going to now multiply those 2 answers together. 1/6 times 2/6 is 2/36, which is 1/18. So this is the probability that this sum is less than 4, given that it's already red. All right, so that can be a little bit confusing. Let me see if I can explain this another way. Basically, we have to have, whoops, I went a little crazy with the eraser. We have to have it have a red 1 is required, and they have to add up less than 4. So out of all the ones with a red 1, it also has to be less than 4. So what did I double circle? Which section did I circle twice? This one, and that is 2 out of 36, which is 1/18th, which was my answer that I accidentally erased. So the answer to this problem is 1/18th. Or you can divide that and get a decimal. All right, let's try another one. Hopefully this will make a little bit more sense. We want the probability, let's see, that the blue marble has a multiple of 3 and the sum is 8. The blue has to be a multiple of 3 on blue. Okay, so let's clean up my chart so I can circle some more here. So which ones have a blue with a multiple of 3? Looks to me like these, because they are 3s, and these, because they are 6s. So out of these, and I want the sum is 8. So now I'm gonna find, well, let me do this. There are 12 out of 36 that have a blue 3. What's the probability of getting, given that it's got a blue 3, what ones add up to 8? Sum of 8, given that it is already a blue multiple of 3. Okay, so out of these, which ones add up to 8? So we've got 6 plus 2. None of those add up to 8, add up to 8, add up to 8, and 5 and 3. So out of those, there's only 2 out of those 12. So now I can multiply this together. The 12s actually cancel out there, so I get 2 over 36, which is 1/18th. Happens to be the same answer as last time. That's just a coincidence, but that is correct. All right, here's one that all these numbers are in the table, so we're gonna try to decipher the information given that other things have already happened. So the table shows the approximate distribution of votes in Texas's 5 largest counties in the 2004 presidential election. Find the probability that a voter from Tarrant County voted for George Bush. So we want the probability that they're from Tarrant County and that they voted for Bush. Okay, so first we need to find the probability that they are in Tarrant County, right? So how many people are there in Tarrant County here? We're going to add these up. There are 559. And out of those, how many voted for Bush? 349. So they had to, that's actually not even an independent or dependent event. It just is out of Tarrant County, how many voted for Bush? Sometimes you get simple questions mixed in with the hard ones and makes them a little bit harder to understand, but that's all they want. So it's really just the probability of Bush, given that they're already in Tarrant County. So I should have written it like this. It's not an and statement. Okay. Second question is more like an and statement. I want the voter voted for John Kerry and was from. So out of all the voters, we want them to be voting for Kerry and from Dallas County. So Kerry and Dallas County. I'm gonna do that. So what's the probability that somebody voted for John Kerry? So you would add up this time. I'm going to change my color. All the voters from John Kerry are 1,422 out of the total number of voters, 3125. Okay, Then for this one here, I want the voters, given that they already voted for Carrie, how many of them are in Dallas County? So there are 336 out of the 1,422 in Tarrant County. So this one is the probability, given that we already know they voted for Carrie, how many of them are in, Dallas County. So we just just multiply these fractions. On big numbers like this, just go for the decimal, 0.108. So there's a 10.8% probability that they were from Dallas County and voted for Carrie. All right, let's do some more examples. And we don't know right now if these are going to be independent or dependent. So it's a good idea to try to wrap your brain around that before you start solving it. So we've got a deck of 52 cards. If you don't know, cards are in 4 suits, and 2 red suits and 2 black suits, and then they go ace through 10, jack, queen, king. So there are 13 cards of each suit times 4 is 52 cards. All right. Selecting 2 aces when the first card is replaced. So I'm going to pull a card, put it back, and then pull another card. So you can't really do 2 at a time unless you're not replacing them. So because it is replaced, is that independent or dependent? That would make it independent because it doesn't affect the second draw. So just think about them as 1 at a time. 1 at a time, how many aces are there for my first draw? There are 4 out of 52. You can reduce that if you want. I'm going to put it back. Now what's my probability of getting a second ace? Again, 4 out of 52. And then we can just multiply and reduce those and clean them up or whatever. This reduces to 3/20. I'll let you divide that if you want to turn it into a decimal. Okay, next up, we've got a face card and then a 7 when the card is not replaced. Not replaced means the second output is going to depend on what you got the first time. So whenever you're doing this, you're going to assume you got what you wanted. So for the first draw, we're selecting a face card. What's the probability of getting a face card? 3, 6, 9, 12. There are 12 face cards out of my deck of 52. And then I kept it. Assume you got 1 face card. You have 1 face card in your hand. Now what's the probability of getting a 7? Well, there are 4 7s, but how many cards are there now? I kept 1 in my hand, so there's only 51 cards left to draw from. Then you multiply this out, and if you'd like, you can turn that into a decimal, but that's what we got there. So you'll hear this in a minute, but I realized as I was recording the next problem that I wrote the wrong answer up here on part A. So I was looking at my notes and I read that wrong. 4 over 52 times 4 over 52 is not 3/20. So maybe we're confused by that. It should be 1 over 169. So this is the correct answer for part A. All right, a few more examples. This one is setup is a bag of beads. So we've got 10 beads total, 2 black, 3 white, 5 red. A bead is selected at random, and we'll decide if they're independent, dependent, and then solve them. So what is this? We select a white bead, replace it, and then a red bead. So for replacing it, what does that mean? It means independent. Let's just read these real quick and see. This one is not replacing, so that's dependent. And this is without replacement. Well, that's the same as not, so that's going to be dependent as well. So we've answered that part. Let's go ahead and solve the problems now. So what's the probability of selecting a white bead? 3 out of 10. And then we put it back, so there are still 10 beads in here. And then I want a red one the second time, so that's a 5. So 3 out of 10 times 5 out of 10, reduce that is 3 out of 20. I think I messed up on the previous slide. I'll go back to that in a minute. So part B, select a white bead, don't replace it. So white bead is 3 out of 10. We already did that, but this time we're not putting it back. So now there's only 9 beads in there. Assume you got a white one. what's the probability of getting a red one? Well, there are 5. So when we do that, we multiply that. It's 15 over 90, which is 1/6. And for the next one, select 3 non-red beads without replacement. So not red. First bead. There are 10 in there. What is the probability of getting not red? Well, there's 5 red and there's 5 not red. So there's 5. I did not. Okay, so assume I got one. I did not put it back. So now there's only 9 beads. And how many of them are not red? Well, since I had to get one that I wanted, there's only 4 left. But I got to do it a third time because I'm pulling out 3 beads. And I only have 3 left in the bag out of the 8 beads that are left in the bag. So then we multiply all of this together and get 60 over 720. That's equals, which reduces to 1/12. And there we have some examples with independent and dependent events.